Hi, everyone. Hi, Shai. So, Australia Crypto Convention. This is my first time in the Southern Hemisphere. It's very exciting. And I chose the title about Crypto 2030. But before I get into the talk, this is a depiction of active nodes of Caspa, full nodes of Caspa, and you can see Sydney is contributing its share. So applaud to, thanks. So an applaud to the active full nodes of Sydney. Yeah, so there's this notion that L1s are not something that the user should be interested at, and that all this complexity of L1s need to be abstracted away from the user. And a recent trend in crypto is that of chain abstraction, which means that we have systems that abstract away the layer 1. The layer 1 is not visible to the user. All the user sees is some unified UI wherein she can transfer her funds seamlessly between layers and to the destination, and there's no need for the user to know anything about the layer 1. Now, as you can see, this trend has picked up, and it didn't really simplify the space. So you can see that in the picture from the rollup, it's kind of the chain abstraction didn't really make it fully simple as you would wish. And I want to argue that we are missing here something crucial, and that is the difference between UI and UX. So as a user, you can have a unified user interface, but and then you won't be able to. You don't need to know whether you are going through a rollup, through Caspa, through a different layer 1. You can just have the same UI. But in terms of UX, I argue that you cannot abstract away the properties of L1. Now, of course, if you completely transfer to a different layer, you can call it L2 if you want, or L3, then you forget about the L1 properties. That's okay. But then we will focus our attention to that layer you are using. So the bottom line of this is, let's ignore the term L1 and simply talk about the layer that's ordering the events, the layer that's sequencing the messages. So again, for me, when we speak about layer 1, I don't really care about the original, culture or meme of that term, but of the actual usage, which layer, which participants are ordering messages. And I argue this is the main role of permissionless consensus to sequence messages, and we will see the properties of this layer. Okay, so can we abstract away the UX? So kind of as a thought experiment, I wanna go, a slight detour and talk about games. So, not less profitable market. And of course, if you play chess, classical chess or rapid chess, before you go to sleep, like I do, then of course you don't really care about the server infrastructure. You move your pieces, you don't care if you lose or win. Whenever the transaction or the move will be sent, you're good. You're losing anyways. But if you're a pro player, all you care, you care a lot about the UX, the properties of the server. So the right analogy here is compare a sequencing layer in crypto to the server infrastructure of the gaming platform you're using. Okay, so they have the same role from your perspective, and you cannot take a pro chess player and abstract away the properties of the server. Okay, you'll basically tell the pro, you'll take Magnus and tell him, you shouldn't care about server latency. You shouldn't care about server uptime. And when you play Blitz, Bullet, Hyperbullet, all you care about is the server responsiveness. Okay, how fast does the server render, respond to your, clicks? Okay, so you can see here a sort of a DAG that Hikaru depicts in this course. And now I suggest we go deeper into this analogy and really compare and list the two metrics. The metrics of infrastructure of servers that you're used to, let's take gaming, we can take any other example, versus the metrics that we use in crypto. And you'll see they're not that different. There's a large overlap. So this picture is kind of my feeling from engaging in conferences. As a layer 1 researcher, I kind of feel everyone has their own stand of tomatoes and they explain why their tomatoes are better. So I have throughput, TPS, I have threshold of Byzantine fault tolerance, you have confirmation times, we all brag about our metrics. So I'm kind of, I hope this convention is less cynical. So I want to push the point that these metrics have an implication to you. So roughly latency, in both systems you have latency. You're interested in latency. You're interested in resiliency against attacks. Of course, in gaming platforms, regular servers, you're more interested in the server not responding fast enough, which is called in technical terms crash fault tolerance. In a more adversarial environment, it's, in research we call it Byzantine fault tolerance, throughput, etc. Now, there are manipulations in gaming. You can manipulate the latency as a player. Now, if you play Fortnite, you can do I think it's a lag switch, where you play with the latency just in order to fool your opponent. So all these metrics are shared across regular infrastructure of servers and crypto. What's unique about crypto and what I want to touch on today is the metric of resiliency to manipulation by the servers or by the miners or sequencers, the agents, the participants of the sequencing layer, whatever layer you want to call that. And indeed, this field has gained traction. In Ethereum, the main DeFi ecosystem, the manipulation by sequencers has come up quite profitable. These are numbers from pre-merge. The new numbers are more delicate, and I won't go into them. So it's a large market, and lots of the activity in Ethereum is around these concepts of server manipulation or miner manipulation, sequencer manipulation, revenue, MEV. Okay, so we set the stage for this metric of resiliency to miner manipulation, to sequencer manipulation. And now I want to take a small detour and talk about Caspa, how it looks today, and how it will look in the future. Hope this works. Not sure. Okay. No. How do I make this video work? Operator, responsiveness, operator. Okay, so you should imagine that there's a live DAG here that's flowing from left to right, and you have here a depiction of Caspa visualizer. If the operator here can click the KGI, that would be awesome. And if not, then just use your imagination You have here a DAG with roughly 1 block per second. And this is how Caspa operates today. In the future, Caspa will operate with 10 blocks per second. Again, if someone here listens, can you please in the back click on here? That would be very helpful. So we wanna we implemented. I didn't really contribute to this. Satan here led the force, the Rusty Caspa force. You can see some of the contributors here. Someone 235, Tiram 88, JWJ, Maxime, quarter of stuff, most of which I'm not familiar with. It's actually open source, and open source vibes and culture. And the vision of 10 blocks per second is that, things become internet speed crypto, internet speed proof of work. So you keep the same ethos, the same principles of Bitcoin, of a Nakamoto system, proof of work, blocks, transactions, all the things you're familiar with, and you are just sequencing the messages differently, sequencing the blocks differently, in a way that is guaranteeing eventual agreement, similarly to Nakamoto consensus. Okay, last attempt. Luke, can you ask the operator to press something? Thanks. Now, so we started with 1 block per second, just, to keep it going. Then Sutton took on the endeavor of writing things in Rust and enabling things to run on 10 blocks per second. And then I was imagining we can run with 100 blocks per second. And now you might ask, what's the benefit of 100 blocks per second? This seems like kind of indistinguishable from the user's perspective, because the human user, has no difference between 100 milliseconds and 10 milliseconds. This is way below our bar of responsiveness. And okay, so I guess that's a no. Okay, so there's an interesting question here. Why am I pushing for 100 blocks per second? So there are 2 reasons here. One reason is that we had a Bitcoin core developer in our team, which was, he worked with us. His name is Elichai. He's an applied cryptographer. He helped us, but he was very indifferent to our achievements. So I had to grind on him and to ask him, hey, Elichai, what would make you less apathetic to Caspa? And he kind of shrugged and said, Bitcoin. And then he said, okay, if you do 100 blocks per second, that will be impressive, and I might be somewhat excited. So that's reason number 1. And reason number 2 is that I argue that you want to have competition between the sequencers regardless of confirmation times. So even if by increasing the network speed from 10 blocks per second to 100 blocks per second, even though the user will not see any difference, noticeable difference in responsive time, in responsiveness, the impact on the competitiveness of sequencing is large. And let me now dive into this. So, everyone has their own tomatoes, as you've seen. And I want to present my own tomato, a new metric, SPR, the number of sequences per round. It's not very sophisticated. I'm basically setting the question, how many sequencers are competing at each consensus round? So what I mean by consensus round is quite simple. In Bitcoin, there's competition between miners, but every block, every 10 minutes, on average, only 1 miner gets to create a block. Similarly, in Ethereum 2.0, I believe 12 seconds is the slow time in which one sequencer gets to decide which transactions are sequenced and in what ordering. Okay, so any blockchain or most blockchain that you're familiar with are leader-based consensus. Leader-based consensus means that whether it's decentralized or not, regardless of the rotating committees and how you achieve silver resistance, at every point in time, at every latency round, so to speak, one entity, one node decides what is sequenced. And you are all fine with this because you're saying, okay, if my transaction doesn't go in the first round, it will go in the second round. So you're not really concerned by this metric. But that's because you're amateur chess players. But if you were pro players, like real DeFi, heavy financial players, traders, LPs, that you want to get the best price for your liquidity, you'll really feel the difference whether the sequencer is one entity that can manipulate everything in that round at will. Just what I mean by at will, front-run transactions, back-run transactions, sandwich transactions, censorship transactions. Just for this round, I can censor transactions, make sure it gets in the next round. So if you were a heavy financial player, you would really optimize you would really enjoy the benefit of competition. So what you see in this graph, you see, again, Caspa, as today, 1 block per second. Let me try to go into details. So this is the newest block. These are the oldest blocks. And I just took a certain slice of the block DAG. And what you see in this slice is 3 miners, 3 sequencers have created blocks in parallel, which is a common phenomenon in a DAG. There's no orphans, there are no orphans, there are no discarded blocks usually. These are 3 miners that, due to the high block rate, haven't seen each other's blocks. This is the name DAG. The term DAG refers to directed acyclic graph, and the implication for you or for the user is that messages can be sequenced in parallel. Now, again, the fact that messages can be sequenced in parallel by every miner at a high speed, of course, is great for confirmation time. But again, if you go from 10 blocks per second or 1 block per 100 milliseconds, this seems like enough for confirmation times. You will feel awesome with Caspa with 10 blocks per second. You wouldn't want more. But I argue that you should want more. So on your left-hand side, you see the testnet of Caspa, a snapshot of this, unfortunately, with 10 blocks per second. Now, you see the implication you see is immediate. You see, okay, faster blocks, more blocks per time, per unit. But more importantly for our context, what you see is more competition on sequencing the round, on sequencing transactions in that round. How does that look like? It depends what mechanism you bake into the system. But I'm working these days with a VVH from the Hebrew University on such a mechanism, and let me give the flavor of the effort. So the flavor of the effort is all these miners, all these sequencers that created blocks in parallel are all competing for your transaction. So consider you are a liquidity provider with large funds. You want to get the best price for your assets. You don't want to be spoofed or the transactions of bots giving you the least favorable price. So how will this mechanism look like? Something along the lines of first price auction, second price auction. I won't get into the details, but roughly at every round, meaning all the time, when a miner creates a block, the miner has to say roughly how much they're willing to kick back to the users. Okay, so I'm creating a block with manipulable transactions I can extract value from, as any sequencing layer can. And now I say, okay, I see that Alice's transaction, gave me a benefit of or a profit of let's say $200. I'm bidding $180 for this transaction. I'm keeping my profit. Another sequencer will be more generous with Alice. We'll give her $190 kickback. And you sort of aggregate these bids, these kickbacks, to decide which miner, to which miner it makes more sense to allow to sequence Alice's transaction. So again, just your mental model should be simple first price auction or second price auction. Of course, in practice, this doesn't work. We need to go into more sophisticated methods. That said, I do want to highlight the importance of 100 blocks per second. So N here in the table behind me, you see a comparison between first price auction and second price auction. All auctions of that sort become more efficient in terms of revenue. Here, revenue would be Alice's kickback as a user. They become more and more efficient as N grows. You know this already. You know that a competitive market becomes more competitive, more efficient, as there are more entities that participate in the competition. This would be kind of intuitive. You start with a monopoly. Monopoly is what happens today in Bitcoin sequencing, in Ethereum sequencing, in Solana sequencing. That's a monopoly. Today in Caspa, you have 2.5 maybe blocks per round, meaning in parallel. So if we had today this system in place, it would be like a duopoly or so, or that of that sort. And if you imagine 100 blocks per second, you'll have a very good competition. So it will be enough for you to send your block, your transaction, to even like 7 or 8% of the sequencers, and you'll get a good price for your transaction. Okay, so think about it in general, more generally. The more parallelized the sequencing is, the more competitive it is, and you can create more products that are basically competing with one another in the same round, in the same 10 or 100 milliseconds. And this might sound petty to you, but actually this is kind of the game in finance. You know that this is the game in traditional finance. These 10 milliseconds are infinity in times of finance, in time scales of finance. People are optimizing for microseconds. Okay, so another problem that is related to that, another challenge, and this will be the conclusion of my main presentation. We are used to think of a blockchain as something that is completely secure, cryptographically verified. Everything in the system is authenticated. We know who signed what, and whether it's true or not according to the input inside the blockchain or the block DAG. However, most of the financial logic actually depends on the system outside, right? You need price feeds from outside to know whether your collateral has reached a certain threshold. This is how Avi lending works. You need to know prices for different assets. And all this data outside the blockchain theoretically cannot be verified. You need to use some economics to ensure, or to hopefully ensure that the system is, that the info is correct. So just imagine a price feed. This oracle says ETH to BTC, I don't remember the range, 1.2. The other says 2.3. All these fluctuations within the same round. You want to aggregate as many price feeds as possible within the same latency, round of the internet, and then you aggregate them in a good way, in a correct way. I won't get into the details now. What's the correct way to aggregate oracles, price feeds, or price feeds or general market data. I will point out that this is a known problem, but not enough known, meaning a lot of the financial logic in our system depends on the oracles, which is surprising because you would have expected, that everything is cryptographically secure within the system. So it is, unless you need data from the outside. And again, 100 blocks per second in parallel system, you can compete, you can arrange a competition between the different agents that are participating in that round and make sure that the competition pushes out outliers, disregards their report, and does averages them correctly. I started a research project with Elliot as a master's student in ETH Zurich, and we are still working on this. Okay, so that's the conclusion of my main talk. So the answer is yes. L1s are still relevant. Sequencing layers are the main thing that is relevant. It will remain relevant forever. You can abstract the UI of this. You cannot abstract the UX. You will always need to inform the user what's going on behind the scenes, what they should expect in terms of other players spoofing them, front-running them, speed of finality. So I hope you join in some form or another the project. Thanks a lot for having me, for having us. It's a great atmosphere here in the hemisphere. See you around.